All right, today we're playing detective. We're cracking one of the biggest, most mind-bending cases in all of physics, the black hole information paradox. Think of it as a cosmic whodunit, where the very laws of the universe are the main suspects. So what's this whole mystery about? Well, it all boils down to a pretty simple question. Let's say you take a book, maybe the most important book in the world, and you toss it into a black hole. What happens to all the information inside? You know, the words, the sentences, the ideas. Does it just get deleted from reality? The answer to that question, it turns out, threatens to break physics as we know it.
You see, the problem is that our two best rulebooks for the universe, well, they completely contradict each other on this. On one hand, you've got quantum mechanics, the master of the small, tiny world of particles. Its number one unbreakable rule is that information can never be destroyed. Ever. But then you have Einstein's general relativity, the king of gravity and giant things like black holes. And it says, nope, black holes are the ultimate shredders. So who's right? They can't both be, can they?
Okay, so like any good detective story, we've got to know the rules of the game. Let's start with our first piece of evidence, which comes straight from the quantum world. And that law has a name, unitarity. Now, think of it this way. The universe is like a perfect bookkeeper. It keeps a flawless record of absolutely everything that ever happens. You can burn a piece of paper, but all the information from that paper, the ash, the smoke, the heat, is still out there. It's scrambled, sure, but it's not gone. Unitarity says you can never, ever truly delete information. It is sacred.
All right, now let's meet our prime suspect, the black hole. According to general relativity, this thing isn't just a vault, it's a cosmic memory wipe. The moment our book crosses that event horizon, the point of no return, poof, it's gone. The black hole itself has no memory of what it just ate. It doesn't know about the book's cover, the author, nothing. All it does is update three little stats about itself: its total mass, its electric charge, and how fast it's spinning. And physicists have this great name for it, the no-hair theorem, basically because black holes are, shockingly simple. All that rich, wonderful information from our book, it just seems to be wiped clean. So for a long time, physicists were kind of okay with this. They figured, all right, the information is just locked away inside the black hole, no big deal. But then, back in the 1970s, Stephen Hawking walked onto the scene and introduced a plot twist so huge it turned this entire investigation upside down. What Hawking discovered is that black holes aren't actually black forever. They glow, very, very faintly. Because of quantum weirdness, the vacuum of space isn't empty. It's constantly fizzing with pairs of particles and antiparticles that pop into existence and then disappear. But right at the edge of a black hole, one can fall in while the other escapes. That escaping particle zips off into space as what we now call Hawking radiation. And over trillions upon trillions of years, this tiny leak of energy means the black hole will actually shrink and, eventually, evaporate into nothingness. But here's the part that blew everyone's mind. This was the bombshell from Hawking's work. His math showed that this escaping radiation is completely random. It's pure heat, like the faint hiss of static from an old TV. It contains zero useful information, nothing about the book we threw in all those ages ago. And there you have it. That's the paradox. If the black hole completely disappears and the radiation it leaves behind is just random noise, then the information from our book and everything else that ever fell in is gone, permanently deleted from the universe. And that is a direct head-on violation of unitarity, the most sacred rule of quantum mechanics. Our two greatest theories were officially at war. So for decades, this was just a massive headache for physicists, an open and shut case where the two main witnesses contradicted each other. But then, pretty recently, scientists found a crucial new clue, a kind of theoretical fingerprint that told them exactly what to look for. So the big question everyone started asking was, okay, let's just say for a second, the information does get out. How would we even know? What would be the telltale signature we'd need to find in that escaping radiation? And this brings us to the key piece of evidence in the whole case. According to Hawking's original idea, the entropy, which is just a fancy word for randomness, of the radiation should just climb and climb until the black hole is gone. That means information is lost. But a physicist named Don Page predicted that if information is actually saved, the entropy would do something very different. It would go up, but only until the black hole was halfway gone. Then it would turn around and go all the way back down to zero.
This became known as the Page curve, and it was the theoretical smoking gun. If you could prove the curve was real, you could prove the information gets out.
And then, just a few years ago, we got the breakthrough. It was huge. Physicists, using some incredibly complex new math, we're talking about things with wild names like replica wormholes, were finally able to do the calculation. And what they found, unbelievably, was the Page curve. It matched perfectly. It was this stunning moment of confirmation. Information does escape. The paradox, at its core, was solved.
So let's just take a step back and look at the case file here. This whole investigation took almost 50 years. It started in the 70s with Hawking's shocking discovery, then came the key clue in 93 with the Page curve, and finally, the case was cracked around 2019. It just shows you how science works, chipping away at a deep mystery for decades. But you'll notice that last point. Cracking one case has just opened up another one. So, let's wrap this up. What's the final verdict from our cosmic jury? Well, the evidence is now overwhelming. Information is not destroyed. Quantum mechanics wins, its golden rule unitarity holds. The information that falls in does eventually get out, deeply scrambled and encoded in the last bits of Hawking radiation, so the original paradox is closed. But a new investigation is just kicking off. How? What is the physical mechanism that lets it out? And figuring that out, well, that's a giant leap toward the holy grail of physics, a theory of everything.
And that just leaves us with this one final, absolutely wild thought. We used to think of black holes as these cosmic destroyers, but it seems they're more like cosmic hard drives. They store information for an unimaginable amount of time, and then they slowly, carefully release it all back to the universe. So the real question now isn't about lost information. It's about what incredible stories about the birth of stars, the lives of galaxies, and maybe the history of the entire universe are written on them just waiting to be read.